Our next speaker will be Thom Dunning. Thom is another EMSL star. He was the first director, and he established our reputation in computation and modeling. The famous Chem code was a leading outcome of that effort. Chem has been downloaded more than 70,000 times since it went open source in 2010. Thom is currently co-director of the Northwest Institute for Advanced Computing, a joint effort of University of Washington and Petascale. Thom.
Thank you. Certainly is a pleasure to be here. As all of the folks in the audience that were here in 1991 and 1992, Don, Tom, John, Ray, it wasn't clear to us that there would be a first anniversary of EMSL, let alone a 20th anniversary of EMSL. So this is really a justification for what it is, the arguments that we made. And in fact, one of the things that struck me listening to the talks yesterday was you might not appreciate at this point how audacious it was for us to make an argument back in the early 1990s that putting all of the instruments and all of the expertise needed to extract the maximum amount of those out of those instruments all in one place was going to be critical to the advance of science. That was a hard argument to make at that point because no one had ever done anything at all like that. And yet what I saw yesterday were case studies. Somehow you ought to make these case studies known to the larger community about what the power of having all of this expertise and instrumental capability in one location can really do. Having said that, I'm going to switch now to talking about Northwest Chem. I'd like to give you a little bit of background on that. My talk's going to be much more similar to what Gene did yesterday than some of the more technical talks that you saw. I'm going to talk a little bit more about the history of Northwest Chem and talk a little bit more about where we're going in the future with Northwest Chem, because it is an ever-evolving activity here. So first on the history a little bit. Back in the 1980s, Ray Baer and I were at Argonne National Laboratory. Argonne had some very good computer scientists like Paul Messina, Jack Dongara, Rick Stevens. And all we were hearing from them was the era of traditional supercomputing is over. We're now going to have computers built out of many, many processors. And in fact, they would point to Cray and they said, Cray, even Cray now is going to multiprocessor machines. So it was very clear that there were big changes in the wind. The other thing that was happening, and the thing that I thought was really very prophetic at the time, Yuan Li, who's a Nobel laureate in chemistry, was giving a talk at one of the DOE contractors meetings. And Yuan Li said, in the past, when there was a disagreement between what was predicted computationally and what we saw in the laboratory, we just ignored it. Wasn't significant. At this meeting, he said, now when that happens, we actually go back and check the experiments just to make sure we're right. So during that 1980 period, there was a big change in the capabilities that were being provided by theoretical and computational chemistry. And that really was one of the reasons that played such a big role in EMSL. Was Bob Marinelli, who was one of the early proponents of this at that particular point, said, we need to have theory, computation, and computing as an integral part of whatever facility that we build in this particular area. So back in the late 1980s, early 1990s, there were a lot of chemistry applications around. There was Gaussian that is still a very popular code today, Columbus, games, but none of them could really take advantage of more than one processor. So if you threw 10 processors at them, they would use one of those 10, and that would be it. At the same time that we were being told by our computer vendors that they'll solve the problem. Their compilers will take care of all of this. So Ray Baer actually put them to the test and quickly found out that, yes, they can do the really low-level parallelization, but they can't do anything very high, and they can't really take advantage of it. I think we did one calculation of which we know was perfectly parallel on 8 processors that ran 8% faster than it ran on one processor. I wouldn't regard that as a truly parallel. So clearly, something was going to be required to adjust to this new world in computing, and it became obvious to us that in fact we needed to have a completely new code, that the current codes that were out there, they just had so much serial thinking built into them that running on a parallel machine was not going to be the right way to go. So we decided that we really needed to really think about building from the ground up an entirely new set of chemistry software that took advantage of these new multiprocessor machines. But this is really a big deal. Even at that time, the codes tend to be a few 100,000 lines of code. So these are very large programs. You'll see that Northwest Chem is actually even quite a bit larger than that. And so we really needed 2 things. We needed funding, clearly. This was something that the EMSL project provided to us, but we were also provided funding from the Office of Advanced Scientific Computing Research, one of their grand challenges. So we had 2 sources of funding for this. $2.5 million a year at that point actually wasn't bad. It's not what $2.5 million a year is now, but back then, $2.5 million a year was actually something fairly significant. So we decided that we would go ahead. Then the question becomes, what do you need to do? We're talking about an entirely new application on computers that almost didn't exist at that point. Just a few computers were around at that point that had this new type of architecture. Well, we quickly decided that doing it traditional way wasn't going to work. We really needed to have a multidisciplinary team, a team that included computational chemists, computer scientists, and applied mathematicians, all part of the same team, all working together toward the same goal. So this was actually, the first innovation that really was critical to the success of Northwest Chem, was this multidisciplinary team. And here, I'll show you a little later the individuals that are, but the real critical thing is they were really working side by side on the development of this new software. It wasn't that the computer scientists were off in one part and occasionally you'd throw a problem over to them. They were in there saying, no, that's not going to work. Here's a better way to do it. Or yes, that's a great idea. Let's implement that. And here's that team. So it was led by Jeff Nichols, although originally it was led by Ray Baer, but Ray eventually became Associate Director for Computing and Information Science. And at that point, Jeff Nichols took over. Jeff is now the Associate Laboratory Director for Computing at Oak Ridge National Laboratory. So you can see the quality of people that we had on this team. Robert Harrison, currently at Stony Brook University and Brookhaven National Laboratory, head of their Institute for Computational Science. So again, Ricky Kendall unfortunately has passed. Cherik Stratsma is at Oak Ridge National Laboratory. Yarrick unfortunately has also passed away. Rick Littlefield and George Fan. And I can remember sitting in my office one day and Rick Littlefield came in and said, I don't understand these equations. Can you explain them to me? And I thought at that point, we got him. He's hooked. He is really a member of the team at that point. The other thing that we had, which was really beneficial in this project, is that we had a tremendous set postdoctoral fellows that were involved in the project. So we were doing a lot of work at that point trying to understand what's the most effective way to parallelize this particular piece of the code. These were the guys that actually bore the brunt of a lot of that. They did a lot of that research work that we needed before we actually understood how it was that we were going to build the code itself. So they played a very essential part. And it really led to a very dynamic environment when you had this core of people and then you had this influx of postdocs coming in, all of whom were enthusiastic, all of whom had a lot of energy and could push the project forward. The other thing we had were a lot of collaborators that were visiting scientists here, collaborators that were from P&L itself, collaborators that were from throughout the United States, and then actually a number of collaborators that were in foreign countries themselves. So you have to remember at this particular time, we were the only group in the world that was saying, we're going to build this code and we're going to figure out how to build it. And in fact, a lot of the technologies that we developed in this process spread out to the rest of the community then as a basis for a lot of the work that we did. But there was an international recognition at this point that we were doing something that was entirely unique, that there was no other group in the world that in fact was attempting this. There was one other innovation in this whole process, and that was understanding the linkage between the software and the hardware. This is something that DOE now often refers to as Codesign. So this you can look at, what we were doing was kind of a forerunner of what it is that DOE is basing its Exascale computing program on, which is this concept of Codesign. So we recognized that in fact, there was a link between what the software needed and what the computer had to provide. So members of the Northwest Chem team actually developed the specifications for the machine, and they selected the machine that was going to be purchased eventually to go into EMSL. And this is that very first machine here. So this whole idea of the software requiring something out of the machine, that was a real new idea at that time. People up to that point had just bought machines. And you had a certain pot of money, and so you bought the machine that money would provide. And typically the focus was always on getting the most cycles, most compute power out of the machine. We said, no, the machine has to have the right balance, and that balance is determined by what the software requires. How much memory do you need? How much CPU do you need? How much I/O do you need? All of this is an intricate balance, and it's tied to the application itself. So this was the other type of innovation that we really had in the Northwest Chem project itself. And so the result was Northwest Chem, a very innovative design at that point, very modular. We were working in Fortran, which was the scientific language at that particular time. So it's hard to do object-oriented programming in Fortran, but we did just as much as we possibly could. And you could see it was built in a layered fashion. And it took advantage of a lot of the innovations that were happening in computer science at that particular point. For example, global arrays was something that was invented in the Northwest Chem project and is used by many, many other applications in chemistry as well as actually in a number of other areas too. So it really implemented a broad range of techniques for describing molecules and molecular processes. It is now, it wasn't then, but it is now 4 million lines of code. But we had one big advantage is that after the project was completed, there was a lot of work that continued on Northwest Chem, and one of those led to something called TCE, which is the tensor contraction engine. And it's really a recognition that there's absolutely no way a human could program all of these formulas that we needed into the machine without making so many mistakes that you would spend a lifetime debugging the code. So Harada, who was here during that particular time, wrote the tensor contraction engine, and basically it does all that for you. So it was the first example of what now computer scientists are calling domain-specific languages. It's something that knew about the physics that went into describing molecular processes, and it spit out the formulas optimized for the machine that it was actually being targeted at. So that's another innovation, later innovation, that came about. As I said, it's written in Fortran. As mentioned earlier, there's 70,000 downloads of the code, more than 3,000 citations in the literature to people doing research enabled by Northwest Chem itself. So this has been really a tremendous success of the EMSL project itself. And it's slowly led to the recognition among the general computational chemistry community that they really had to think about how it is their code runs on parallel machines. There are still not a lot of codes out there because as you can see from this, it is a big effort to write an entirely new code like that. So there are really surprisingly few codes out there even now. And Northwest Chem is still the only one that can really take the leading edge computers at DOE and run them full tilt. At the same time, we had this code, we also needed to have the compute hardware to run it. And so there's been a succession of computing systems in EMSL to support this kind of activity. Each of these computing systems, as you can see, was of greater and greater computing power. Many of them ranked highly on the list of top 500 computers in the world, but I would stress that was never the goal of what we were trying to do. These machines were optimized to do the kinds of research that was being done in EMSL. They were in no way trying to target, we want to be such and such on the top 500 list. It just so happened that that was the case. So what has all of this led to? One of the things that I would always get when I would give a talk at DOE or at the National Science Foundation is, you guys are always asking for more computing power. What does this really mean? And so I actually got around to answering that question at one point. I went back through the literature and I looked at how accurately we can compute bond energies. Now, bond energies are actually one of the most difficult challenges that we had in computational chemistry to get reliable predictions for. But if you look at what's happened over time, and remembering I started back before 1970, back at that point, if we had 100 kilocalorie per mole error in a bond energy, that could be typical. Nothing unusual about that. But you see, as a matter of time, in fact, a decrease in the error from those calculations. And in fact, at this particular point, for molecules that can be treated with the highest levels of theory, we can actually do better than you can going into the laboratory and doing the experiments. We can predict those bond energies more accurately than you can get from the experiment itself. This, of course, was not a result of any one particular thing. It was new theoretical approaches, new mathematical techniques, and of course, at the end, more computing power to be able to solve these very complex equations that we have to solve. My wife asked me one time, what is it that you have spent your career doing? And I tell him, well, there's this one equation called the Schrodinger equation, and we're trying to solve it. I should have had a picture of it, but one time we were at Cambridge and she found a Winnie the Pooh with H psi equals E psi on it. And her comment was, it looks like a really simple equation to me. You spent 40 years trying to solve that equation. So the other thing that's happened, though, is not only can we compute some quantities much more accurately than we could in the past, but we can actually compute much more complex systems themselves. We can make predictions on much more complex systems themselves. Back when I first came to PNNL, Dave Feller was doing some work on the water dimer, and this turned out to be really a benchmark set of calculations here on the water dimer. It really tied down completely the bond energy, the hydrogen bond energy in the water dimer. But that was stressing the limits of what it is that we could do at that point. Then back in the 1990s, Satiris and I started looking at water hexamers. Whoops. Water hexamers. So much more complicated systems, more computing power available to us at that particular point. But we were still running up against the limit. I mean, we were stretching everything to be able to do these kinds of calculations. So after Northwest Chem, what's available? These are the kind of systems that Edo and Satiris and others have been looking at. So much more complicated water clusters than we had been able to look at before. So just look at that chain going all the way from dimers stretching what it is that we could do in the early 1990s to what it is that we can do now in the 2000s with the capabilities provided by Northwest Chem. So now we know that DOE is pushing on into the exascale computing era. Clearly, this is a new technology that we need to master, but there are going to be lots of innovations that are going to be required to do that. And here is their co-design philosophy. If we had put up there HPCS1, we'd put here global arrays, we'd put over there Northwest Chem. You can see they're following exactly the paradigm that we followed back in the 1990s with the development of Northwest Chem itself. And of course, very different machines. We're now talking about machines that are hundreds of petaflops of computing capability. I should say very different kinds of machines. They're looking at basically two kinds of architectures. One at Oak Ridge that has very powerful but very small number of nodes on the machine. The one at Argonne is each node is less powerful and there are a lot more of them. So kind of the two extremes that you have in looking at petascale computing architectures. Well, the good thing is that Northwest Chem is now one of the projects being funded by this. We're calling it Northwest Chem X for exascale computing capabilities. So we're completely redesigning and re-implementing. So it's a process that we went through back with Northwest Chem itself. We did not take any existing codes. We redesigned Northwest Chem right from the ground up and re-implemented it completely. And we're doing exactly the same thing now because the changes in the computing hardware, the changes in the computing technologies have been so great that just trying to rewrite Northwest Chem isn't going to be sufficient. So we're completely redesigning it. And of course, we have a whole new set of problems now that all of you are tackling. We're trying to understand about what controls the transport of of atomic ions like calcium-2+ across membranes. Because this is the process, this is the way that plants react to stress. And if we can understand that better, we may be able to push plants or design plants that can grow on more marginal lands. Or looking at new catalysts for the conversion of these biomass into biofuels, something that right now is very energy inefficient. We need to be much more energy efficient. So what are we doing? As I said, we're completely redesigning and re-implementing Northwest Chem or the exascale computers. So we're going to address the limitations of Northwest Chem itself, the design, the algorithms, et cetera. We're actually going to switch the code base to C++ away from Fortran because that gives us so much more flexibility. We now have a real object-oriented language that we can use. We're going to target those two problems that I mentioned. And also, we're really interested in now developing the framework that the whole community can contribute to develop a whole new set of capabilities that we don't even imagine for Northwest ChemX, but the larger community has a need for. Here's what the project looks like. So this is the organizational chart. And if you look down through here, you'll notice many familiar names. All of these individuals have one way or another been connected with Northwest Chem, whether it's Teresa Windus at Iowa State, who led the Northwest Chem team here at one point, Robert Harrison, who was the chief architect originally. But we have a lot of the current staff. Also, Carol Kowalski, Edo, Opera, Eric Bilaska, Neri, et cetera. So this is bringing the Northwest Chem team back together and completely redesigning what it is that we did originally for this whole new set of extraordinary exascale computing technologies. And this just gives you a timeline of where it is. It's a 4-year project, so we're looking at 4 years from now having this capability available for use. And I just wanted to end my talk remembering Bill Wiley and Bob Marinelli, whose name has not really arisen very much here. But here are the two co-conspirators whose vision of EMSL, at that time it was called the Molecular Science Research Center, or more colloquially in the laboratory, the money-sucking research center. But these are the two individuals who really said, first, that molecular science is critical to understanding many problems in the DOE mission. And there really should be a facility that brings all of it together, the state of the art in experiments and the state of the art in computing, to really make the advances that we need to solve these particular problems. So with that, I'll end, and if there are any questions, I'd be happy to answer them.
So you showed that graph that with the accuracy and
yeah.
experiments. At what point did that gentleman make the prophecy that now we rely on the computational model?
So that was the 1980s. So that was we could predict bond energies at that point to errors of several kilocalories per mole, so 4 or 5 kilocalories per mole. But we also could do much better in predicting trends, and that's the thing that he was most worried about, is that we could do much better at predicting trends than absolute values at that point. And so if he got a different trend than what we were getting, he worried.